Hello everyone, we're Team 3. We'll be presenting the optimized design for manufacturability of a COVID-19 ventilator.
Ventilators were in high demand during the pandemic to help people breathe. The design uses a 3D printed frame and a motor to achieve this function.
Here's a quick view on the assembly CAD that shows the base view of the product. Now, the exploited CAD shows the details of the product. There are a total 27 unique parts that go in this design. Please use the table on the left as reference for the names of parts. Here's the motor assembly breakout view as it shows combined in the exploded CAD. It sits right underneath the bottom support, and there will be a switch on the display panel that's connected to the motor. Our primary customers for this product would be hospitals or medical facilities that use ventilators to supply sufficient oxygen to patients with restricted breathing. Secondary customers for this product include ambulances for when a ventilator is needed in the field.
The ventilator fast diagram is shown below with the task function of assist respiratory system, the primary functions of adjust pressure and enclose air, as well as the supporting functions.
Next, the team created 2 assembly sequences. We tried combining components based on their interactions first and came up with assembly sequence 1. For assembly sequence 2, we tried refining the subassemblies and moving components around and moving sequences around that better fit manual assembly. The noticeable difference between the 2 sequences is the ease of fastening and the ease of testing subassemblies. The combining of the bases and moving the lower squeeze subassembly after the motor subassembly allowed for an easier overall assembly process.
Here we have the function component mapping matrix, where each component of the ventilator is mapped to a leaf level function from the fast diagram. The presence of multiple components within a single function is what drove our redesign efforts in terms of DfM and DFA.
The breakdown of the ventilator's BOM is shown below. The initial design results in approximately 262 seconds assembly time and a cost of $311.40 to manufacture. Next, the quad matrix shows the component classification. Please note that the components in the High Cost and Importance tab will not be redesigned due to them being purchased. The components that will be redesigned will be discussed in an upcoming slide.
In terms of functional differentiation, the 2 variants are quite similar. The only function that differs between customer groups is support attachments. As shown on the component commonality table, the only parts that will be different between the 2 variants will be the 4 display supports.
The primary difference between the mobile and the non-mobile variant is the hole added in the front plate for easier transport.
The original product family assembly diagram is shown below with the original added handles. The modified assembly sequence is shown post-DfM with the combined display assembly without the handle cutout as the primary variant and the display assembly with the cutout as the mobile variant.
To improve on the 11.5% assembly efficiency, the team chose a set of module and platform parts for redesign as shown below. Comparing these to the quad chart, we see that these parts individually have a low manufacturing and assembly cost, but with the number of parts that can be reduced, we believe it will overall help the efficiency. For the module part redesign, we combined the 4 individual display supports into one sheet metal formed part. This allowed us to meet DFA 1 and 5 to reduce part counts and variety, and also DFA 7 to facilitate part orientation. By meeting these points, we're able to reduce the assembly time by 25.53 seconds.
For our design for manual assembly platform parts, we chose the ball nut and pivot pusher from the motor subassembly. Again, adhering to DFA 1, we consolidated the parts, removed the 4 fastener holes on the ball nut, and then achieved alpha symmetry with the resulting part shown on the right. Creating this part reduces assembly time by about 3.5 seconds, presents no changes to the component's functionality, but will have some extra costs associated with the threaded hole in the new part. After completing design for manual assembly, we have eliminated 5 unique components, reduced the assembly time by 41.48 seconds, increased the assembly efficiency to 13.4%, and also reduced the total assembly cost by $6.50.
For design for automated assembly, we chose the motor subassembly. All the components in this subassembly support the function of adjusting pressure. The 3 small components that we use for automated assembly are the ball nut, pivot pusher, and motor mount. In the table on the bottom left, you can see that this total cost comes out to $31.83 for the full subassembly. To reduce the cost of automated assembly, the ball nut and pivot pusher was redesigned. We used the same redesign techniques as manual assembly, which was DFM1 reduction of part count, DFM2 removal of fasteners, and DFM3 increasing of part symmetry. The new automated cost is $10.49 and a savings of 67%.
For modified parts, we decided to keep the original material, metal, due to its durability. To ensure optimal performance and cost effectiveness, the process selection criteria considered were material, shape, section thickness, tolerances, surface roughness, and economic batch size. Using the process selection matrices from our class, sheet metal working was identified as the most suitable manufacturing process for the module. For the platform part, die casting emerged as the best option.
The base profile tolerance ensures the part's overall form and dimensions stay functional. Critical dimensions like hole sizes, threads, hole locations guarantee proper alignment. Non-essential dimensions fall under the base tolerance and they don't affect assembly functionality. The most critical dimension on this part is the profile of the acme threads. A tight tolerance on these threads is essential to ensure proper functionality. Precise tolerances are also required on the rotating pins to snugly fit within the bushings, minimizing slop and ensuring smooth rotation.
The first step in design for manufacturing was the die casting cost. The first cost calculated was for the combined ball nut and pivot pusher, which will use a screw mechanism. The total cost for this part was 79 cents as compared to Part Finder, which was $1.26. The discrepancy in this cost was due to the complex design used as an example. Once the cost was calculated, we put the design in DfM Pro and redesigned it. The first three suggestions were the draft angle 5 degrees, the wall thickness inconsistency, and the sharp corners. The designs that were not taken into consideration were the thread draft angle and thread minimum wall thickness, since we're going to use a screw device and we felt DfM Pro did not have the correct suggestions. Here's the 2D drawing and the redesigned isotropic view after the DfM Pro suggestions.
Display assembly sheet metal working cost was calculated utilizing the analytical method. Material cost was calculated at 40 cents per part, machine operating costs were $1.58 per part, and die cast costs were 5 cents a part, assuming a 1-year payback period. Hubs extrapolation was calculated at $3.57 per part. This is 57% more expensive than the analytical method, likely due to the more expensive material utilized in the Hubs analysis and the relatively small extrapolation dataset. DfM Pro was then utilized to analyze the design, and 4 major guidelines were violated. Hole distance to bends, cutout distance to part edge, cutout distance to bend distance, and min-bend radius rules were all violated. Here's a drawing of the front display assembly before DfM showing critical geometries. Design for sheet metal guidelines 4, 8, 9, 10, and 11 were utilized to guide key design revisions. The sheet metal thickness was reduced to 22 gauge steel to satisfy min-bend radius requirements. The base width was increased by 6 millimeters to allow the tab width to be increased to maintain critical interface geometry. Tab height was increased, and the holes were moved away from the edges while maintaining interface geometry. The analytical method was then utilized to calculate the sheet metal working cost post-DfM. The material cost was calculated at 26 cents per part, machine operating cost $1.58, and die costs 51 cents per part. The total revised part cost was $1.89, a savings of 14 cents. Hubs was then utilized, and an extrapolated cost estimate came in at $2.88 per part, a 69% cost reduction. Here's a drawing of the display assembly showing critical geometries post-DfM. A pay-per-use fee structure can be implemented to charge the hospital or mobile consumer on a per-hour basis of ventilator usage instead of the hospital or mobile consumer purchasing the ventilator up front. This per-hour fee structure would allow already produced ventilators to be shared with facilities without producing new ventilators by charging the hospital or mobile consumer a monthly fee for possessing a ventilator but not utilizing it. This would encourage facilities to give up excessive ventilators, thereby saving the production of a new ventilator and the environmental impact associated with it. Additionally, recycled plastics and metals will be utilized to produce the ventilator when possible, and an end-of-life recycling program will be implemented.
The key outcomes of our analysis and redesign efforts for DFA and DFM are summarized on the left. Reflecting on our design, the team recognizes the need for further DFM and part consolidation on the remaining ventilator components. It would have also been beneficial to recognize the unnecessary fasteners and complex geometry of the initial design earlier on in our process.